Welcome back, everybody. This is part 2 of the Intro to Limits notes, sections 1.1 and 1.2. So we're going to jump right into the notation and then start working on some examples. The notation is going to be pretty much the same always. We're going to have to add in a little bit of nuance to it, which we'll discuss as well, but this notation is going to be pretty much the notation that we use throughout whenever we're describing limits. So on this page here, we'll kind of break it down piece by piece. So the first part of our expression is the expression that actually uses the word limit or part of the word limit. So we have this limit as x approaches a, where a is some real number. And just as a side note, for calculus, the single variable calculus course, we only deal with real numbers. We don't deal with complex numbers. The calculus of complex numbers is a course that you can take in college, but for us, we're going to focus on real numbers and real value domains only. So a is some real number. Our function input x is going to be approaching that number. So the limit as x approaches a of f of x. So we have to essentially declare what are we taking the limit with respect to. So we're taking the limit with respect to this function f of x as the domain value approaches a. And we give it an arbitrary value L, where L is also a real number. So it could be 6, 12, pi, negative 1/3, square root of 2, any sort of real number that we can think of. So the limit as x approaches a of f of x is equal to L if, so there's a big if here, and if we go back to the wording that I put in the notes, if we can make the values of f arbitrarily close to L. Okay, and for our course, we're not going to get super rigorous on what that means to be arbitrarily close. So there's a method of describing limits using what we call epsilons and deltas. But we're going to say if we're sufficiently close to that value of a, whatever number we end up with is going to be what we call the limit. Now, there's going to be cases where as we get closer to a, we don't approach a single value. So note, L is a single number. So you can't approach multiple numbers and have a limit exist. A limit has to be approaching a single numerical value. Okay, so again, if f of x approaches L as x approaches a. So one way to think about this, so we had that example of that function. So if this is a, as I'm getting closer to a from either side, so from the left and from the right, what we're saying is that the function itself, say L is here, is going to be approaching L as well, right? Whatever our function looks like. So it doesn't matter what our function looks like. As we approach along the x-axis closer to a, we approach along the y-axis closer to L. So if we look at the example that's drawn here, we actually get a pretty interesting example here, because we'll make a note of something. This function has a hole, and that hole is at the domain value we're approaching. So there's a hole at x equals 2, but we still say that the limit as x approaches 2 of f of x equals 4. So why? Why do we do that? Well, because what a limit is describing is what happens as we get arbitrarily close. And that's the key. So I want to put this down below as well. So describes the behavior of f as x approaches a. So note, not what happens at x equals a. So our limit is describing the behavior as we get really, really close. But we actually don't care about what's actually happening at a. Right? Because clearly we can see we're going to have a hole, which is a type of discontinuity in the graph. So the graph has two pieces now. But if I look from the left and from the right, the behavior is exactly the same. It is approaching 4 on either side, even though f of 2 does not exist. Right? 2 is not even in the domain of this function. But every value arbitrarily close to 2 is in the domain of this function. So that's the key, is that we're describing all the values around x equals 2. And in particular, we want to get as close as possible. Right? So the goal is always to get as close as we possibly can. And one note is the limits on either side have to be the same. But again, the function doesn't have to exist at that point. So again, jumping over to the other note here, so a function with a hole at a, limit exists. Now, what do I mean by the limit on the left and the right has to be the same? Well, I could have a graph that has a jump discontinuity at a. And in this case, we would say that the limit does not exist, or D and E, you can shorthand it, because the limit from the left is not equal to the limit from the right. So those two values are not approaching the same numerical quantity, so the limit doesn't exist. The limit exists from the left, and the limit exists from the right. So we're going to have what we call one-sided limits. So for this example, let's say this is 2, and this is 10. All right, so we would say that the limit, as x approaches a from the left, we'll put a little minus sign. So this is from the left of f of x is equal to 2. And the limit as x approaches a from the right, which we'll denote with a positive sign, is equal to 10. However, those two values are not equal. So the limit as we approach a does not exist, even though the two one-sided limits do exist. Okay. So again, for these intro sections, they're going to focus on you making tables. So we've got these two examples here. So it says using a graph or a table, using a table. So what I'm going to do is actually describe a more algebraic approach to evaluating these functions. But again, say for number 1, what you would want to do for number 1 is you would want to look at, if I'm taking the limit as x approaches 1, you want to take values close to 1 on the left. So I'm going to pick values smaller than 1. So 0.9, 0.99, 0.999. And then I'm also going to pick values that are just bigger. And then you're going to compare those numbers that you get by putting that in a calculator or using Desmos. and see if they approach a value. But this approach is kind of weak because it requires a bit more work, right? So it requires you to calculate some points. You could maybe just calculate points really close, but you want to be careful because there will be some functions where maybe these two numbers are the same, but this number is different. So we have to be very careful when using a graph or a table. And graphs won't always be accessible, right? So all of the work that you're doing right now should be without a calculator unless it specifies to use a table or graph. You should check all of your work, however, using a graph at least, I would recommend. But I want to show you an algebraic approach. So if I look at this expression, this is a rational expression, and we know how to simplify rational expressions. So we'll just note x minus 1 over x squared minus 1 is the same as x minus 1 over x minus 1 times x plus 1. So we can factor the denominator using a difference of squares, which tells us that this is really equivalent to 1 over x plus 1. Of course, our graph will have a hole at 1. But again, holes don't matter. Holes don't matter in terms of our limits existing. So that means that the limit, as x approaches 1, of x minus 1 over x squared minus 1 is really the same as the limit as x approaches 1 of 1 over x plus 1. Okay, so if that's the case then let's think about that graph, right? So we know there's going to be a hole at that point, but does the hole in our graph matter? It doesn't. So if I know that this function is not going to be a jump discontinuity, and it's also not going to be a vertical asymptote, then I can use what we call direct substitution, which we'll focus on in the next section in a lot more detail. But I can literally plug in the limit value into my function expression. And what we'll end up with is 1/2. So again, you could verify this graphically and you should end up with 1/2. The same will be true for the second example, only now we wouldn't have a factoring method to use because this is not a factorable expression. But there is something we can do. And note, that should be a t, is if we have a radical expression, we can attempt to rationalize it. Now, we shouldn't do that first, though. So let's note the limit as t goes to 0. Radical t squared plus 9 minus 3 over t squared. Let's suppose we just plugged in 0. So if we plug in 0 to our function, we would get the square root of 9 minus 3 over 0 squared, which is 0 divided by 0. That's a problem, because 0 divided by 0 is an undefined expression. We don't know what that means. And so you might say, okay, well, maybe the limit doesn't exist, right? 0 divided by 0. Well, what this is actually going to mean to us is that more work is required. So we're going to have to do a little bit more analysis to figure out, because 0 divided by 0 could mean that it doesn't exist, but it could mean that it does. So I'm going to erase that. It's not erasing on the bottom, but that's okay. So we're going to try and figure out an analytical way to look at this. And so if I have a radical expression, one option I can always try is to rationalize it. So that means I need to multiply by the conjugate. So the conjugate is going to be the difference of squares expression in this case of whatever our term looks like. So I'm going to change the -3 to a +3. And then I can't just multiply the numerator, I also have to multiply the denominator by that. So let's see what happens when we distribute. So on the top, we'll have a difference of squares expression. So the radical t squared plus 9 times itself will simply give us t squared plus 9. And then -3 times +3 would be -9. And then this will be all over t squared times the quantity radical t squared plus 9 plus 3. So now if I simplify my function a little bit, I can see that the 9s are going to cancel, which means that I end up with t squared over t squared times the conjugate expression. Put the 3 down here, smush it together a little bit. But then also, we get some cancellation. So what we get from our work here is that our original limit is equal to the limit as t goes to 0 of radical t squared plus 9 minus 3. Oop. We can just write our new expression. So our new expression from the right is simply going to be 1 on top. So 1 over the square root t squared plus 9 plus 3. And again, what I can try to do here then is once I'm at that point, now I can try the direct substitution step. And what I'll get is 1 over radical 9, because it'll just be 0 squared plus 9, plus 3, which gives me 1/6. All right. So let's see if this actually works. Let's go to Desmos. And let's create that function. So y equals square root. I'll use x squared here. So again, variables can be interchanged for letters. And we'll call this h of x. Okay. So if I look at that graph, which is here, let me get rid of the other graphs. Okay. So we might want to zoom in a little bit. Clearly, if we zoom in, what we get is Desmos's best approximation to the nearest thousandth here, it looks like, is 0.1667, which 1/6 is approximately 0.1667. So that is showing us what that limit looks like. Again, it's very easy to graph in Desmos, so definitely check your answers that way. So going back to our notes, we've got our first two examples worked through. We've got our definition of limit written here, and I would really emphasize what we discussed at the start, which is using the notation and remembering that a limit describes the behavior as we get really, really, really close on either side, from the right and from the left, and it is not about what is happening at f of x unless we have some type of a discontinuity. So we'll get into more details next time, but if you do have questions, send me an email.